that changing one line meant that you had to look at all the other lines before it and all the other lines below it for the whole program. Now, those programs, I mean, if they didn't have many lines of code, yes, they worked. And then uh, their functionality was limited. So maintenance of and even understanding that program was very difficult. Then later on came subdividing a program into smaller chunks which were doing specific things. And this is where we started using functions. So you'd split a program into smaller components, and those smaller components were called functions, and they would do specific things. Then this evolved into improving functions. Function had its own data and it had its own logic. So in other words, they became what are called objects, which were fairly independent. So if you wanted to change a program, you didn't have to look at all the code. You only went and looked at the object that you wanted to change. Now, later on, this object evolved in such a way that an object could do a specific task. So, in other words, the object changed such that they became autonomous. Autonomous simply means they are not dependent on something else. So this is what we mean by software components, and this is what we mean by autonomous. Now, platform agonistic, in other words, when objects evolved to be autonomous, then what they did is that they were not dependent on a particular platform. So platform agnostic means they don't have to be aware or on which platform they were going to run. They didn't have to know that I'm running on maybe this operating system or I'm running on this compiler. That is what platform agonistic means. And then an ecosystem of services. It means these autonomous software components, which are agnostic, instead of creating one huge monolithic program, you just created components. And in these components, you could put many different components working together and end up with a good program. So this is where programming has actually now gone, where you find people don't create huge monolithic programs. People just create components which you can link together through APIs, and they work together and you create an application with the functionality you require. For example, Microsoft Office. Sometimes you can buy a version, a Word version that doesn't have the maths component to do calculations for you. But what you can do is that you can install that maths component if you're a mathematician. And then when you're writing a document, you can include very complex software by simply calling that maths component. Now, if you are in geography, you can call the Google Maps component where you want to show direction to somebody, or even generally, when you are writing a document, it's possible for you to call the Google Maps component, and it's going to do something for you. You can call the drawing component, and it can do something for you. So what has happened is we have created what is called an ecosystem of services. So you'll find that each component is giving you a particular type of service. Like the maths component is going to give you the 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 the, the mathematics, uh, a mathematical service. The Google Maps component is going to give you a mapping service. The drawing is going to allow you to draw. So we are calling this an ecosystem because you can find different people can create different applications or different components that do different things. So what you need to do is that you just call that application so that it gives you that service that is required. But what that means is because you want people to call these uh, components so that they work together, they must have certain standards. So there are standards that are associated so that when you create mapping, also when you create an application to help you with maps, then you must put an interface which anybody who wants to call it is going to use you are giving. So that is what we mean by a service. So the ecosystem, because we are calling it an ecosystem because it's made up of thousands of many different components, is going to be governed by what is called the service-oriented architecture. So technology is the use of services for software development. So what happens is you will find that different people have created different autonomous components. Now, you are from scratch. What you do is that you'll call in these different services and you'll put them together, and out of them you'll get a very complex application. But this complex application, it's not you who created it. All you did is that you used logic and you are calling these components and you are making them work together. And once they work together, they bring in some level of complexity. So this is what the service technology does. And these components now offer services. So you just call them, they do something for you, and then you release them. So service-oriented architecture is a new paradigm that actually came up with the cloud computing, which is an architectural style that focuses on discrete services instead of a monolithic design. So remember when I just started, I said that in earlier programming, you created a program and the program executed sequentially. And if one line fails, the rest fail. But then I said then later on, you split that program into functions, which means different people could create different functions. Then later on, the functions evolved to become objects where you had the logic and the data. And then from objects, it has moved to services. So services are discrete. In other words, they are not tied to each other. So in other words, you'll find that 100 people can use the same service because it's an autonomous component, so they can just make a copy of it and use and reuse it. So it relies on the composition of loosely coupled services to achieve complex functionality. So we are saying that these components are not tied to each other. You just call them, they do something for you, and you could release them, or you make a copy so that they'll repeatedly keep doing something for you. Now, this is what, in a way, software-oriented architecture is what, in a way, has led to the evolvement of AI. Remember, AI is not something that started recently. But in the past 3-4 years, you've noticed that AI has developed so much. So people keep talking about AI. Like the VC, the chancellor, uh, tasked the university to come up with an MSc in AI. The reason being that AI has now become a very hot topic. Now, why? It's because for a long time, people are developing AI in discrete components. You would find somebody doing a neural network, another one doing a computer vision, and so on. But now these days, these components are discrete components. So what is happening is programmers, and especially young people like you, are going out there and they are looking for packages that have these components. And what they're doing is that they are mixing different packages and they're working together and they're coming up with some very complex functionality. And this is now making AI look like it is real. So that is an example of a service-oriented architecture. So the service technology laid the foundation for as a service cloud delivery model. Typical realization and construction of service technology of cloud computing are done through the web service, representational state transfer service, and service agents. So service technology, under service technology, the technical standards of web service include the following. Now, remember, we've said, yes, we have an ecosystem, but for this, from this ecosystem, for you to put things to work together, then there must be standardizations. In other words, when you are creating a component, you must have a standardized way of how commands will be sent to your service. You must have a standard way of how commands will come out of your service. And this is going to be followed by all components, so that all components have standardized way of sending out data or commands and receiving data or reacting to commands. So some of the standards include what is called the Web Service Description Language, which is a markup language used to create web service description, WSDL definitions. And now what are these definitions? They define the application programming interface of web services, including its independent operations or functions, and input, output messages for each operation. So it tells you how to create functions. In other words, it tells you how to write the logic, because a component is going to do something. Now, for it to do something, it must follow some logic. Like maybe you are creating a calculator. Calculator is going to do addition, division, multiplication, and so on. Now, those are functions. So there must be or let's say it's a calculator. A calculator should be able to do all those things together. So it gives you standards for writing that logic. And it's also telling you how you can send data for that computation and what the output, how the data is going to be output. This is specified under the WSDL. Then we have what is called the XML schema definition. So the XML schema definition are messages exchanged by web services. In other words, the messages exchanged by web services are generally expressed in XML. I'm sure by now you know what XML is. HTML, yes, HTML is a language for writing web pages. But this language has standard definitions. But different people may want variations. So XML allows you to come up with user-defined or things which are specific to you, where you don't have to be tied to particular definitions. So the XML schema definition language is a language used to describe the XML schema. And what is an XML schema? An XML schema defines the data structure of XML-based input-output messages, which are exchanged by web services. It can be directly linked to WSDL definition or embedded in the WSDL definitions. So that is service technology. Then we have two other additional things which are defined under the service technology. We have simple object access protocol. So, like I've told you, an object is a software component that is fairly autonomous because it has its own data structures, it defines its own data, and it defines the logic. So SOAP is a protocol that defines the general message format of the request and response messages exchanged by web services. A SOAP message consists of a header, generally contains metadata that can be processed at runtime. Metadata is data about data. Like if you say an integer, metadata is defining what an integer is, because an integer is data. So metadata is a description of what an integer is. And then a body. So SOAP is, just like the name suggests, is a simple object access protocol, because you have an object. Now, an object does specific things. So you'll send a message to an object and ask it to do certain things. But you see, an object has logic and it has its own data. So you'll tell an object, take your data, do this operation on this data, and give me output. So it's simply like a command, commanding an object to do something. But remember, an object is fairly independent. So the object will take its own data, use that own data, and depending on the command, act on that data logically, and then give an output. Then another part of the service technology is the universal description, discovery, and integration protocol. The protocol stipulates that the server must register and publish the WSDL definition to the service catalog so that users can discover that service. So depending on the commands, objects will do different things. So the different things that an object can do have to be registered so that the user knows that this object can do 10 services. So that must be registered in the server where the objects are stored, so that the server knows if the service is there, it will give you, you'll have access to the service. If the service is not there, it will tell you as much. So that is the service technology. So the above four technologies form a classic web service technology, and the relationship is as shown. So it's showing the four things, and it's showing their relationship. Now, when you are reading this diagram, keep notice of the direction of the arrows. So like the UDDI is a discovery service, and it communicates, it sends message to the WSDL, and so on. The WSDL does binding to the SOP. So what I want you to do is to take this diagram and take these descriptions, and then that will help you understand this diagram. Then representational state transfer service. SOAP and WSDL are complex technologies. So what came about is what is called uh, uh, REST, Representational State Transfer Service. REST is now a lightweight and concise software architecture style that can reduce the complexity of development and improve the scalability of the system. So in other words, REST is able to do what SOAP and WSDL can do in a lightweight way. So mainstream cloud service providers are increasingly adopting REST style design and implementation to provide web services. For example, Amazon offers REST style web services for book searches, and Yahoo provides REST style services for web services. So REST services do not have an independent technical interface. They share a common technical interface called uniform contract, which corresponds to a set of architectural constraints and principles. So REST, for you to use REST, then there are certain standards that you must know. So it's not independent whereby it's going to operate on its own. So an application or design that meets these constraints and regulations is called REST. REST is usually based on existing widely popular protocol standards such as HTTP, URL, XML, HTML. Now, these are standards that are associated with developing web applications. So if you have to implement REST, then you will need to know these four. And by now, I'm sure you already know them because you are already doing your project. Then the other one is the service agent, which comes under service technology. Now, a service agent, remember an agent, anytime you say you are having an agent, you can have human agents. You send an agent to do something for you. Now, let's say you're transferred to a new town that you've never been to before, and you need a house. You don't know that town. You don't know the rates, the rent rates. There's the least you know about that town. Now, for you to get a house, it means you have to know some things about that town. Then it will take you time. It will take you time to know those things. Then after you've known those things, then you'll start now searching the house. Now, but because you want to save on time, you will look for a housing agent, which is a human being. You'll give him as he'll make his quote. You'll give him a fee. He'll search for a house for you, and then he'll show you the house. So you are giving him some tasks to do for you, and he's giving you the results. But now in cloud computing, what we do is we use software to do that. There are people who write software to go and do things for you. Like you could have software to do management. You could have software to do configuration. You could have software to do monitoring. So these are specialized programs that do specialized tasks. So a service agent is an event-driven program which intercepts messages and performs related processing at runtime. Now, event-driven simply means that most of the time it is in the rest state. In other words, it's idle. The only time it executes is when a certain event occurs. Like when you tell it to execute, then it will execute. Or you could set it that when a certain time comes, it executes. That's what it means by event-driven program. So cloud-based environments rely heavily on service agents to perform most tasks such as monitoring and metering. These service agents are customized to accomplish specific tasks such as elastic expansion and such as pay-per-use. Elastic expansion you could send it to tell it to increase memory. You could send it to tell it to create a virtual machine. Then you could also tell it to do metering for you, monitor how much time a client has been using a certain task, do the calculation and tell you what you need to charge that client. So service agents are divided into two. We have passive service agents and active service agents. Passive service agents do not modify the content of the message, but after reading it, it captures the specific content for monitoring, recording, or reporting. Active service agent intercepts and reads the message, and it may take certain measures such as modifying the message content or the message path. Both are common in cloud-based environments. And that brings us to the end of that lecture. That is cloud enabling technologies. So you've looked at these technologies. Now next, we now start looking at the system. Now remember, here we've been talking about technologies, and we've said the technologies evolved independently. Now, when we start talking about a system, we are now saying that a system is made up of many components. Now, this, for us to call it a system, it's made up of many components. But these components are using different technologies. So when I start talking about cloud computing system, I'm basically talking about the infrastructure, the physical infrastructure of the cloud. Now, an infrastructure is made up of many things that are interconnected. Like for the cloud, we have computers being connected together via a network. Now, computers utilize their own technology. Networks utilize their own technology, different technology. But now here we have, for these computers to communicate, we need to link them. So we could call that a communication system, a computer communication system, which is made up of two technologies, the computing technology and the networking or data transfer technology. So this is what we are now going to look at. So in a way, what we are looking at here is how these technologies that I've talked about, the 6 technologies that I've talked about, can now work together. So because it's a huge topic, I have divided it into computing into 3 lectures. So today we are going to look at cloud computing system 1, which is the cloud infrastructure mechanisms. So at the end of the lesson, the learner should be able to describe and explain the features of cloud infrastructure mechanisms. So what is a cloud computing environment? And this is under the cloud infrastructure mechanism. A cloud computing environment is a complex IT resource integrated system that has some basic building blocks called the cloud infrastructure. So to come up with a cloud computing environment, we must have some building blocks. Building blocks simply means we are bringing different components together. And when we bring these different components together so that they work together to do something, we refer to it as a cloud infrastructure. So these facilities are the basis for building a basic cloud environment. Now, the 5 main cloud infrastructures include the logical network boundary. Now, this is using the networking technology, the virtual cloud server, which is using the virtualization technology, the cloud storage device. Remember, we talked about we talked about data centers, the cloud usage monitoring. Remember, we also talked about utility computing, where you ask requests for services, your usage is monitored, and you are charged as per your usage. Then we talked resource replication, where we talked about multi-tenancy. We talked about multi-tenancy, where many users could be using the same application. Again, we talked about one processor via virtualization. One processor is being used by many people, and they are not aware that they are using one processor. So we shall look at each of these infrastructures in turn. So all these come together to come up with what we are calling our cloud. Now, these things are now physical realizations of what I've been talking about what I've talked about in the previous lecture. So the logical network boundary is regarded as a relatively independent area. Now, I mentioned yesterday that sometimes we find it difficult to understand concepts because we read the fine prints without understanding the heading. So what does logic, when we say logical network boundary, what do you exactly mean by the term logical? Now, by now, okay, I'm sure you did data communications, which I thought, and you must have done computer networking. Now, in networking, we have multiplexing, where we share a physical channel. So in multiplexing, for example, you can have, we know that any communication needs a pair of wires, which could be twisted, or you need a simple fiber strand, or you need a frequency. So let's use an electrical link, for example. In an electrical link, it's possible to physically see a pair of wires. But using time division multiplexing, you can have 24 pairs of computers communicating. So what you'll do is that you'll create 24 time slots, from time slot 1 to time slot 24. And you can decide to give the first pair of computers time slot 1, the second pair of computers time slot 2. So what it means is that between 0 and 1 microsecond, the first pair communicates, or they have the full access of the pair of wires. Then from time slot 2 to time slot, from time slot 1 to time slot 2, you have another pair of computers, and so on. And you could do the same thing. For the same pair of wires. So using time slots, what happens is that the different pairs of computers are given different time slots. So you'll have to wait until your time slot reaches before you transmit. But it's possible using frequency division multiplexing to have the 24 people communicating at the same time by giving them different frequencies. Now, as long as the frequencies are not similar, they can communicate. So this is an example of a logical network. So we have one physical network, but we have 24 logical channels. So that is what we mean by logical. So logical and physical have different meaning. Physical is what you see, logical is what you don't see. So in communication, then we can have 24 pairs of communication, either at the same time or at different times, but using the same physical link. So we call those logical channels. Now, similarly, using switches, now this is in networking. You can have one switch, physical switch. Now, let's say if this switch has many ports, let's say it has 24 ports. So physically, you can see one switch. But in a local area networks, you can have 3 networks. So physically, there's one switch with 24 ports. Logically, you have 3 networks. So that each network has 8 machines. And the data in one network will only be, if the 8 networks are in one network, only those 8 networks can see each other's data. Now the others are using the same physical switch, but they cannot read each other's data. So we have 3 logical networks, but 1 physical switch. Or you could have 2 switches interconnected, and you have machines on one switch, and you have 3 machines on one switch and 5 machines on another switch, and you create a logical network. So there are 2 physical switches, but we can have 1 logical network, but 2 physical switches. So what I'm struggling to say is that logically is how data moves, but physically is what you see. So that is virtual LANs. Then virtual private networks, you can use the internet. You know, the internet is not owned by anybody, but you can create a network using the internet, which is a public resource, but by using virtualization, using the VPN software, you can have a network made up of 10 people in Kenya and 5 people in the US. They are using the internet, which is a public resource, but to them, that network appears as if it is theirs. So again, that is logical. So VPNs apply to the internet. VLANs applies to local area networks. So VLANs are implemented via switches. VPNs are created via encryption. So logical network boundary is regarded as a relatively independent area. When we say relatively independent area, it looks to you that it's yours, but ideally it is not yours. Relatively independent, it's only those people who are in that particular area who can communicate. So a logical network boundary isolates a group of related cloud-based IT resources from other entities in the cloud. Now, just like in a LAN, I've said if you have a switch with 24 ports, you could have 3 logical networks. So you could put finance in one logical network, put lecturers in another logical network, put students in another logical network. So physically, they are using the same physical device, but logically, their data is fairly independent. So most times you create these logical groups for groups that are related. So in a cloud, that happens. Like we said, we have a public cloud, we have a private cloud, and we have a community cloud. So you could do that, allowing people with the same interests to share cloud resources. So the resources in a logical network boundary may also be physically distributed in different areas. So just like I've said, using this switch, examination personnel are located in one building, lecturers are located in another building. So you'll find that using a data center, they'll share that switch. They'll share the switch, but they are in different physical locations. Where locations don't necessarily have to be buildings, they could even be towns or even countries. So this is an example of 2 logical network boundaries, including cloud users and cloud service provider. So as you can see, here we have an internet or a VPN, and you have a cloud user network. Now, you see, this is a cloud. Cloud, they could be physically in totally different locations. And here we have the cloud service provider network. So you could find that your cloud service provider is in Australia, but you have created the cloud user network in Kenya. So because of the geographical distances involved, the transfer of data is going to occur via the internet or via the virtual private network, because the VPN applies to the internet. So you create a virtual firewall. You create a virtual firewall because virtual firewalls is a combination of hardware and the software. So it could be one physical machine, but you are running a virtual firewall on that one physical machine. So this cloud user network has what is called a logical network boundary. Now, why logical network boundary? Because the people who are using that cloud may be in different buildings, or they may be in different parts of the town, but they are in a community cloud. For example, University of Nairobi and USIU is doing collaborative work. They decide, why don't we create a cloud community for this collaborative work? Let's say we are working on an AI application. So we say, we want to use AI for teaching. So let's create this application between us. So we will create a community cloud. But University of Nairobi and USIU are far away from each other. They don't share the same buildings. They are different places. But using the web technology, we can create our user network for that particular thing. But for us to do that, we will need a cloud service provider. So what we are saying is a logical network boundary means that we don't have to be physically situated in the same place. Now we need a virtual firewall because we are using the internet. The internet has millions of users, so we don't want people interfering in the work, and we don't want if any of us is not ethical, we don't want any of us doing unethical things and sending them to the internet. So this is where the logical network boundary comes. So to provide a virtualized isolation mechanism, there must be corresponding network equipment. So what we mean by corresponding network equipment is that we must have servers, physical servers, and we must have software. Yes, Edwin.
Thank you, sir. So, is this similar to the aspect of creating a walled garden or a geofencing, in the sense that servers can be only accessed within certain parameters, like within certain geographical boundaries, or within a logical place that has been determined by the people setting it up?
Okay, I don't know, but okay. Think about this way. There's physically what you see, and there's physically how the data moves. Like I've given you the example of University of Nairobi, where I'm saying in the University of Nairobi we have we our data center is in Chiromo. So in Chiromo you'll find that where you have your lab, where you have your undergraduate lab, there's a room there where you by the way, that room rarely manned. You'll find that we have a lot of switches there. Now, what these people can do, what they have done, is that they have created uh, virtual local area networks. So you will find that the examination at the examination center. Now, that examination center houses people who are only dealing with exams. So I'm sure you know that the examination center where sometimes you do exams. Now, physically, those people are situated together. Then you come this block where we mainly are, where the head of department and some of our offices are. We are put together. So physically, I don't know whether they've implemented it that way. Physically, we have okay, yeah, that's a good example. There are certain things you can't do unless you go physically to Chiromo. Like for a long time, I could not, uh, I could not access I could not update or request for my leave electronically. I had to come to the University of Nairobi. So the technical section has created a VPN for the university community, and this VPN can only be used if you are physically within the University of Nairobi. But externally, you can't. Similarly, I was talking about the examination. They have created a virtual private, a virtual local area network for the exam, meaning it's only people in the exam who can access that network. And to access it, they have a web-based interface to access it. Now, the same thing with the university health services. It is being administered centrally from Chiromo, from the data center in Chiromo. So you can see we are physically dispersed. The exam center have their own room where their staff are. Now, why they are put there physically is because they may need to talk to each other, just the same way lecturers need to talk to each other. But you'll find that lecturers and the people in the exam center, we rarely physically talk. The only thing is that, for example, when we want an exam to be printed, then we'll send an exam to them. So the concept of virtualization is this: you have the physical hardware. So in the university at the data center is where we have the switches, and those switches we normally use layer 3 switches to clear those to create those virtual networks. So what I'm saying is, and I don't know whether I'm answering you, is that
Yes, I'm following.
physically you don't have to be in the same environment. And it's possible that when I'm doing collaborative work with another researcher in the UK, it is possible that we can decide to contact a cloud service provider to create a cloud for us. So I am in Kenya and somebody is in the UK or US. We are doing collaborative work. We are storing data in one place, but physically I have never met you. I don't even know how you look like, but we are doing work together. I can talk to you via the internet, and I can store data in a common place. So differentiate between the physical appearance and the logical appearance. And that's why I started talking about time division multiplexing, frequency division. So the issue of logic comes in whether you are talking about networking or whether you are talking about computation or whether you're talking about memory or storage. And sorry?
For example,
Yeah.
when you look at Google Cloud Platform, I normally use it, and Azure and AWS. The issue, there is the aspect of there is the logic aspect whereby when you set up a, let's say, a server on Google Cloud Platform, they will tell you
Yes.
to choose where this server is going to be located physically. You can choose China, Beijing, even South Africa. Then once
Yes.
you choose that location, it
Mm-hmm.
means that the server will be running in a physical machine that is physically located, let's say in Beijing,
Yes.
physically, but
Yes.
logically it is accessible globally. Now,
Yes.
uh, you can choose there's another server on the same Google Cloud platform and put it in a different physical location. But now
Yes. Yes.
the servers are they can access each other globally within the Google Cloud platform. So when you configure it like that, there are some aspect of that server that are only accessible let's say, if a server is running in Beijing, it will have some properties that a server that is running in China won't have, and that is now configured logically. And that is what I was trying to ask. Is it the same thing?
Yeah, exactly. Yeah, it is the same thing. And now you are being, you see, and you've chosen you've chosen Google. Google is a good example. Google does many things, and one of the things that it does is to provide cloud services. So what Google has done is, because it's an international company, it puts spots, or it has places where it has its physical stuff, and there are places where it doesn't have its physical stuff. So, like, you may find it cannot afford to have stuff in all places in Kenya. Sorry, in all places in Africa. So Google may choose Kenya as a country where it will have a skeleton stuff, and it will put some servers in Kenya, which hopefully will serve Kenyans. Then it will go to another continent, because it wants to have a global presence. It will go to another continent, and it will choose a certain country, and it will put some skeleton stuff there, and it will put servers there. So that's one of its core businesses, to provide cloud services. So what we will do is that, as different countries have different ICT policies, Like I mentioned, like China, some doesn't have some strict policies on intellectual property. You go to Chinese sites and you download books. Now you go to the US, they are very strict on intellectual property. Stealing somebody's intellectual work is very serious in the US. In China, they just let it go. Now you look at the US, they are very open. You can talk about, call him anything. Go to China, you cannot talk about their president or insult him or draw cartoons about him. There's limited freedom of speech in China as compared to the US. So why Google wants you to do that? And you see, Google is doing business. It's international. It is subject to the policies and laws of the country in which it operates. So when it gives you a choice, if you are very well conversant with these policies, you may want to know, okay, I would rather store my data. If I'm developing an application, I would rather store it in the US because then it's not likely that somebody is going to get that application and make copies of it and give it out freely or sell it cheaply. But in China, I know that is going to happen. So what Google does, because of the fact that it is international, like you have rightfully said, it has servers in different countries, which are conducive to its business interests. And this is also because it's doing business. It doesn't want to pay money to a lot of people. So it will have servers in different countries, but the way it uses those servers is subject to the policies of those countries. So here you are, Edwin, in Kenya. It asks you, where do you want to store your data? Now you will say you'll choose US. Now, how your data is handled is subject to the policies in the US. So it is as if logically you have a presence. Your data in the US is accessible to people who are in your cloud. But physically, you are very far away. You are 8,000 kilometers away from where your data is stored. I don't know whether that's answering you.
Yeah, completely. At least now I understand it better.
Okay. Fine. So we move on. So we are still talking about virtualization. So to provide a virtualized isolation mechanism, there must be corresponding network equipment. So then the network equipment usually include the virtual firewall, which can actively filter the network traffic of the isolated network and control its interaction with the internet. Remember, for the internet, I said we use virtual private networks, and we could use virtual firewall. Now, a firewall is a combination of software and hardware, because the firewall software is stored in a computer, which is hardware. Now, for that computer, you could make copies of that virtual software for different for different clouds. That's what we mean. And for virtual firewalls, basically should be run by the cloud service provider. So we are saying it's actively filtering the network traffic. In other words, it prevents malicious programs or malicious information coming into your cloud or it prevents you sending out malicious programs or malicious information. So that is what the virtual firewall does. And then a virtual network, which is generally formed by virtual local area network. And I've told you, for local area networks, we usually use we use switches, and we layer 3 switches to create what are called virtual local area networks. So you'll have, depending on the number of ports, you may have 3 or 4 networks on the same machine. Now, this is because these switches can do filtering. They can block information from one segment of the network from going to another segment of the network. So physically, you are on the same machine, but logically, you cannot access each other's data. But for the internet now, we use VPNs. So the logical network boundary is generally deployed as a virtualized IT environment. The figure in the previous slide, this figure, shows 2 logical network boundaries: the internal enterprise environment and the cloud environment. So the internal enterprise and enterprise environment contains the cloud users. The cloud environment belongs to the cloud service provider. The 2 logical network boundaries are connected through the internet or a virtual private network. So advantages of using a virtual private network is that the data between the two parties can be encrypted and the communication content can be protected. So I think later on I should modify this diagram. So what it's showing is that it's showing 2 virtual boundaries. There is the logical network boundary for the service provider network. Now, okay. Now I'm going to link this to what Edwin has asked. Supposing, like Google, I have a server in China, a server in Australia, and the servers in America. You can see these are 3 different continents, which are many kilometers apart. Now let's assume that Google only has servers in those 3 continents. Now, these servers cannot be connected they cannot be interconnected by private links. It's going to be very expensive for Google to try and connect China to Australia, Australia to America, and America to China when they form their cloud. They cannot physically run those links. They will not manage it. So what do? They use the internet. So they use virtual private network software to connect China to Australia, Australia to US, US to China. So they are using the internet. But you see, the internet doesn't belong to anybody, and anybody can transmit data. So what the VPN software is going to do is that it's going to use the internet, which are shared links. The internet basically uses multiplexing. So it's going to encrypt data from China to America, America to Australia, and so on. So they form a network, a wide area network between 3 countries. And they are now using the virtual public network technology. So that is what I'm now referring to as the logical network boundary. So Using VPN, they've created a boundary. They've created a cloud made up of servers in 3 different countries. So physically, they are dispersed. Logically, they are connected. In other words, they are using the same data. Now, that is what I'm calling a logical network boundary. Now, here is Edwin and Eric. They are working on some collaborative work. So they request Google, who has servers in 3 different continents. They request for a service. They tell Google, we want to create a community service. We are doing this research. Can you enroll us? Can you create for us a cloud? So they'll create the cloud. Now in the cloud, because they are interconnected in 3 components using virtual links and VPN technology, our data, the data we are working on, could be in any of these 3 countries. And that's what Edwin was asking. When you want to create, you'll be told, where do you want it to be hosted? So we may decide, let it be hosted in Australia. Now, we are in different places. But Google has created a cloud for us. So we are calling that, because it's the 2 of us working together, and when we are working and a cloud has been created for us, nobody else can access the cloud. So there is a logical boundary that is created around us that only allows the 2 of us to work together. Nobody else can have access to that data. So this is what we mean by internal enterprise environment and cloud environment. So the 2 logical network boundaries are connected through the internet or a virtual private network. So I've said we've looked at the advantages of using a virtual private network. The logical network boundaries main function is network segmentation and isolation to ensure relative independence of the IT facilities in the area. So once a cloud is created for you, then it isolates you from any other people. So you may not be physically near each other, but logically you are near each other. You are within the same boundary. So the network infrastructure needs to be virtualized before the logical network boundary forms a virtual network layout. A virtual firewall based on a physical firewall is used for network isolation. So, for example, an enterprise may divide its entire network into an internal network and an external network. Just like I was telling you, in Nairobi, University of Nairobi, we have our VPN, where you may not access anything unless you physically go to the University of Nairobi. So an enterprise's internal network is a virtual network isolated by the internal firewall and can only access resources within the internal firewall. Like if I want to read the newspaper, when I go to that University of Nairobi website, I can't from my home. But if I go to the University of Nairobi and I log on to the University of Nairobi network, then I'm able to read the newspaper. So that is an example of how virtualization works. So as an example, data in the internal data center network cannot access the external network and the internet. The external network located outside the external firewall is directly connected to the internet. So what I was saying, there are certain things I can access in the university and there are certain things I can't access in the university because our technologies have created those virtual, they've created both the virtual local area networks and they've created the virtual private networks. So the area located between the external firewall and the internal firewall is called the demilitarized zone, or DMZ. So the DMZ is abstracted as a virtual network, which generally includes the proxy server and a web server. The proxy server is responsible for coordinating access to common network services like DNS, domain name service, email, and the web. And the web server provides web page access functions. So an institution's network can be divided into three logical network boundaries: an extranet, an intranet, and the DMZ. Extranet allows the University of Nairobi to communicate with the people it's closely associated with, like suppliers and so on, anybody that the university is dealing with. We use an extranet. An intranet is for the university community, for communication within the university community. An extranet is for communication between the university and the people who the university is closely associated with: contractors, suppliers, bookshops, and so on. And then the demilitarized zone is a virtual network that basically includes the proxy server and the web server. So, any question on the logical network boundary? Okay, so we look at the next. So now here we are dealing with the actual implementation of the technologies that we were looking before. So the other one is the virtual server. The virtual server is a server that is virtualized on a physical server using virtualization software. Now, in virtualization, remember, I introduced the virtualization technology. I said in virtualization, the application's monopoly of physical resources is avoided, and the same physical server can generate multiple virtual server instances. So in a single computer, what happens is that when an application is using a certain resource, maybe it's using a processor or is using memory, then it has sole access, and other applications will have to wait for it to finish, to terminate, before they can access those resources. And this is coordinated by the operating system. But where you want, and you see, in that case, most times, the capacity is not utilized 100%. In fact, only a small fraction of the processor and a small fraction of the memory is going to be used. Now, what does virtualization do? Virtualization creates another layer on top of the operating system. Now, this layer creates simulators, where the simulators simulate the processor, they simulate the memory, and so on. So, in other words, and you see, this is software-based, so you can create many copies. So what happens is that then many applications, different applications can use these different copies. So physically, you are seeing one server, but logically, you have created 10 versions of that server, because you've created simulators for the processor and simulator for the memory. And this is what we mean that an application's monopoly means that only that application can use that physical resource. So by providing independent virtual server instances to cloud users, the cloud service providers can use limited physical servers and other IT resources, and improve resource utilization efficiency. So Google has 10 servers and it has 100,000 users. Google cannot provide 100,000 servers. So what Google is going to do is that it's going to create, out of the 10 virtual servers, is going to create 100,000 virtual servers, which are actually just software. So Google can now serve 100,000 people. Now, this is what we see, is that it can use limited physical servers and either IT resources. So Google can't give each person its own server. So it's going to use virtualization technology, where it's going, on the 10 servers, it's going to create 100 virtual servers. Now, for each server, let's say one server is handling 10,000 people. So that server is now going to be utilized efficiently, because in any case, the 100,000 people are not going to be working at the same time. But you'll find that if somebody comes, he's not denied a service. So the most basic building block of a cloud environment, the virtual server is the most basic building block of a cloud environment. Each virtual server can allow access to a large amount of IT resources. It can allow you to access CPU, memory, external storage, and network. To facilitate users to create virtual server instances, cloud service providers or users usually prepare some customized virtual server images. So remember, we've said we use virtualization software, which creates a simulator. Now, this simulator comes with the very basic services. There are some fundamental services it comes with, and then you can create a copy of this software, and now you can customize this copy according to your needs. So to create a virtual machine, a pre-customized virtual machine image is used. So pre-customized means it comes with some basic and fundamental functions, but now it's you to work on it and improve on it. For example, we have what is called the Huawei. Huawei has a virtual cloud server, which can be regarded as a customized virtual server image, where each product generally specifies the number of virtual CPUs contained in its corresponding virtual server instances. And it has specific performance instances such as clock speed, memory, network bandwidth, and so on. So these are the things that you are going to customize. So creating a virtual server instance from an image file is a resource allocation process that can be completed quickly and on demand. So resource allocation, we have one physical server, 10 people are requesting. So you create 10 virtual machines for them. And because this is software, it can be done very quickly and it can be done on demand. So for example, we have two virtual servers in the image, in the figure, are based on the same physical server, and they can provide services for different users. So this is a physical server, what you are physically seeing. And like I've said, the virtualization software is a layer on top of the operating system of this machine. So this machine has an operating system. When you want to do virtualization, you create another layer. Now it's on that layer that you are going to create a virtual server. Now you can see it's gray because it's not something that you can physically see. If you wanted to physically see it, you'll only see this machine. Now, this person can customize his server according to his needs. And this person can also do that. And they will not interfere with each other. So under the virtual server, we have what is called the virtual machine monitor or VMM software, which usually runs on the physical server. Now it controls and manages the virtual servers. Then we have the virtual infrastructure manager or VIM, which is also known as virtual device manager, which is used to coordinate work related to the creation of virtual server instances. So the manager is going to manage the various instances. So if you create 10 instances, those 10 instances will be managed by the virtual device manager. So this is an example. So here you have one physical server running 3 virtual servers. Here we have another physical manager running 2 virtual servers and another physical server running 2 virtual servers. Now, virtual servers need to be managed by the virtual machine monitor. So, because there are 3 of them, they need something to manage them. And this is what we are calling the virtual machine monitor software. Now, it's software that is running on top of the operating system, because now there are many, so there needs to be software to manage them. Just like the operating system manages the resources within the physical server. Now, if they are on the same cloud, then we shall have what is called the virtual infrastructure manager, because virtually they are connected to the same cloud. So what happens is that we have an infrastructure, a virtual machine infrastructure, or a virtual infrastructure manager. So this virtual infrastructure manager is software that manages the various virtual machines. So we have software here, the virtual machine monitor here. We have one software here to manage this, another software here to manage this, another software here to manage this. But because they are in the same cloud, there is a virtual infrastructure that needs to be managed. Now that virtual infrastructure is managed by the virtual infrastructure manager. So virtual machine images are usually stored in common cloud devices as files, say this software. Cloud service providers or cloud users can prepare virtual machine images with the different hardware and performance specification for users to choose according to business needs. So Huawei Cloud website, the ECS, which I defined here, Huawei provides many types of virtual machine images for different user needs, such as for general computing scenarios. So you can configure your virtual machine for general computing scenarios, for memory intensive scenarios, for high performance computing scenarios, for big data, and for computing scenarios. Now the category also contains a large number of subcategories giving different CPU memory ratios, virtual CPU quantity ranges, base frequency, turbo frequency, network speed, application scenarios, and other performance or product parameters. So cloud users can choose the most suitable product according to their needs. So that is about the cloud servers, virtual cloud servers. So, okay, Roman. Yes. Okay. Let- Yes, Muhali.
Can I try to answer him? But I'm sure I'm going to get it wrong.
Yes, yes, please. Go ahead. Yeah, go ahead.
A virtual machine images work like this. According to my perspective, when you deploy a virtual machine and say you set up, let's say, an operating system, then configure, let's say, some software in it, maybe a custom software. Uh, you might want to create multiple virtual machines. And then now what you would want is to, each time you're creating a new virtual machine that probably is going to be doing the same thing another virtual machine was doing, instead of installing the same operating system, setting up the same softwares and doing the same configurations, you can create an image. It's like a photocopy of a virtual machine that you've already created, so that when you're deploying another virtual machine, you can just replicate the other virtual machine now as a new virtual machine. Uh, but maybe that is in a different context. The lecturer can clarify.
Yeah, you're muted.
Yeah, I'd already finished giving my 2 cents. I don't know if I was cut off even before I explained. I finished at the point of creating the replication of another virtual machine.
Okay, but I've been hearing you throughout, Edwin.
Yes.
Yeah. So anyway, what I wanted to do is to use this diagram to explain to him further. So this is a physical server. Now, so this is just a normal machine. I mean, it's okay, it could be a normal machine or a specialized machine, but it has all the components of a computer. It has a memory, it has a processor and so on. So what you do is the cloud service provider will, using the virtualization software, uh, simulate this machine. In other words, he will write software that works the way this machine works. So basically, a virtual machine is software which simulates how the actual machine works. Now, if you remember, when I started this course, or when I started talking about virtualization, I talked about simulation. And one thing I said is that supposing you are doing research on the internet, you cannot uh, physically do it on the internet because the internet is not owned by anybody. So there's nobody you'll ask permission on how to use the internet. And secondly, if, for example, you're doing research that involves intrusive software like viruses, you are not going to introduce viruses to the machine because physically to the internet, because it's going to inconvenience other people. So what you do, if you are doing research, you will create a simulator of the internet. So you will capture all the functionalities of the internet in software. So you run that simulator on your machine, and then you start introducing viruses into your simulator and seeing what the simulator is going to do. And by the way, creating a simulator is a very complex thing, but people have done it. Like for the internet, we have NS2, NS3, we have Omnet, and so on. We have different types of simulators that simulate how the internet works. So these simulators are used by researchers. So what happens is that for you create a simulator of the server. Now, a simulator is just basic software. Sorry, it's software that tries to mimic or imitate how this server is going to work, but it is software. It's not a physical machine. So let's say I'm the cloud service provider. I create a simulator of this server, and I'm running it. I'm running my simulator on this server. So these two people come and they tell me they want to use some service on this server. Now, what I'll do is that I'll make a copy for this person and I'll make a copy for this person. And that's why we are calling this a virtual server. So physically, these two people will get the services that this server is giving. And to them, it will appear as if this server is solely their own. What they don't realize, they don't even know each other, and they don't even realize that physically they are using this one server. So there's the basic machine, virtual machine that is created by the cloud service provider. So they create the basic software, the basic simulator. Then that simulator, because it's software, you can create 10 copies of it. And you can give the 10 copies to these different, the 10 different people who are requesting to use this server. Now, these 10 different people will not know that physically they're just using one server, because that server is being imitated by the software or the virtual machine that has been created by the cloud service provider. Now, why that is possible is this. Most times, we don't utilize the full capacity of our machines, like your PCs. You will realize that by the time you're buying a new PC, you have only probably used 10% of the memory. You realize that anytime you are doing a task, you are not utilizing the full processor power. So that is one. Most times, for most machines, we do not utilize their full capacity. Then secondly, you will find that most times the 10 people are not working on that machine. And this is where the issue of scalability comes in. And that's why people come in and people go out. People come into the cloud and people move out of the cloud. But because the 10 people will not normally work at the same time, then again, you shall find that most times we do not reach the full capacity of that server. So basically, that is what virtualization is. So physically, we have one machine, but we are using simulators. And in the case of computers, we are calling them virtual machines. But virtual machines are simply files. And when I talk about files, we are just saying these are software which can be stored, and you can make many copies of those files. I think that is how I can explain it. I don't know whether it makes sense. Yeah. So, okay, it's 1:01, so we'll let us stop there for today. Let's meet next week. Please tell the others to attend.